time-aware auto-white balance in mobile photography. The colors of photos we see on our digital screens are not their original sensor measurements, but the result of a series of image processing steps. When light reaches the camera sensor, it produces a raw image that is linearly proportional to the number of photons incident on it. The raw image has a color cast due to the interaction between the illuminance color and the sensor's spectral response. The raw image is then processed by the camera's image signal processor, the ISP, which transforms it into the final display image. One key component of the ISP is auto white balance, which removes the unwanted color cast in the raw image. Auto white balance typically involves two steps: estimating the global color tint expressed as an RGB vector and applying a diagonal correction to neutralize the color cast. Modern illuminant estimation methods often rely on neural networks to predict the illumination vector. Since the color cast depends on the illuminant's color spectrum, any change in the scene illumination results in a new color cast. Most methods estimate the color tint directly from the raw image, often guided by color features extracted from it. We observe, however, that time of day provides an additional strong cue for illuminant estimation. As the sun moves across the sky, the spectral composition of daylight changes accordingly. To refine this further, we incorporate geolocation. Relying on clock time alone is insufficient, since the same time of day can correspond to very different sun positions around the world. For example, in the summer, sunset happens much later in Toronto than it does in New Delhi. Geolocation information helps align timestamp with the corresponding solar event. By combining timestamp and geolocation, we compute a probability distribution over solar events, for example, sunset and sunrise, indicating the likely illumination condition under which the image is captured. We also use metadata available from the camera to distinguish between capturing environments, such as indoor versus outdoor. In our model, the time of day probability vector and capture metadata are processed into one feature set. In parallel, image histograms provide scene color information. Both are fused in latent space and pass through a series of linear layers to output the estimated illuminant vector. Since no public dataset contains raw images paired with time location information, we build our own. Our dataset spans diverse indoor lighting setups and outdoor weather conditions with an enriched set of metadata. Our method achieves accuracy comparable to state-of-the-art models, yet requires only about 5,000 parameters. In addition, we provide additional ground truth data to broaden the dataset's impact for other applications. We provide two illumination styles, including a neutral ground truth from a color chart and a user-preferred ground truth, seven rendering styles, and denoised raw images. In summary, we leverage time of day, geolocation, and capture metadata to achieve a lightweight auto-white balance solution. As part of our contribution, we provide a large-scale dataset of raw images with contextual metadata and multiple illumination and rendering style annotations. Thank you.